So good morning. Let me hopefully be the first but not last to welcome you to Geography Awareness Week. Today is our first day in a series of workshops and other events we're doing in celebration of this annual event. Today's workshop, we're going to be looking at working with spatial data in Python. My name is Molly Webb. I am a GIS developer on the data services team here at Olin Library. And my job here as a GIS developer is to help staff, faculty, students incorporate geospatial data and spatial thinking into their research. I work a lot with Python, and so I thought that it would be good to offer just this little kind of intro look at working with spatial data in Python. So we're going to do a little intro stuff on Python first. When to use Python. So the whole point in using Python to automate working with spatial data usually comes into play when there is a particularly complex process or a process that you need to run over and over again on similar data. So it always is a balance between how long is it going to take you to, say, write a script to do the task you need to do versus how long is it going to take you to do it maybe on a desktop GIS, and then where do you want to spend your time? What makes the most sense? So chances are if you have kind of a recurring processing task that you need to do, you might want to consider learning a little bit of Python and automating that process. There's lots of different options for working with spatial data. The primary one that most people are familiar with is working with a desktop GIS. So you have your ArcMap, your ArcGIS Pro, which are licensed applications. You have QGIS, which is an open source cross-platform desktop GIS. And there's some other lesser known ones, but those are the main desktop GIS systems that are being used out there today. There's other Python libraries for working with spatial data, most notably the ArcPy library, which is an API for the ArcGIS Pro application. So you do have to have an ArcGIS Pro license in order to use that library, but it can be really helpful. We're not going to cover that one today because I wanted to focus on open source libraries today, but that is a very popular Python library for working with spatial data and tools. And then another one that I like to use is R and RStudio. That combo, more and more, they have pretty robust capabilities for working with spatial data, and then even cartography as well to create your finished map products. How we're going to access our workshop materials today. We have a Google Colab notebook and then some additional files. So let's take a look at how we can get to those. I'm going to go away from my slideshow here for a second. And then this is the link. When you click on the link, the share link, you're going to see something that looks like this. And what I'd like you to do is on the workshop data folder, go ahead and right click and click download to get those files downloading to your local machine. And then we're actually going to run the notebook here in the web browser. So I'm just going to double click on this link, and that's going to open up this Colab notebook. If I look in my downloads folder, I can see I have a zip file of my workshop files here. I'm going to right click and I'm going to go to 7-zip, or you could also do the extract all, and I'm going to extract that zip file to get my workshop files. Just to take a look at what we have here that we're going to work with, we've got 2 zipped shape files here. If I click into this file, I can see that it's not just one file, but it's actually made up of a combination of files that all work together. These files are all together referred to as a shape file. You don't need to unzip those right now. We're going to go ahead and work with those just as the regular zip files. So you can leave those as is. I've got a couple of CSV files here. We've got a list of Planned Parenthood health centers, their addresses. And then we've got another file that is just a couple more records with alternate addresses, and we'll cover those a little bit more later. And then the last file we're going to look at is a health report for 2020. This has health data for all of the counties in the United States. And we've got some different geographic identifiers here that we're going to use. All of the data are in these SE columns going across the top. And to know what these columns are, there's a data dictionary that is included here. So you can look up the different variables that we're going to use. The variable target in question we're going to be using for our analysis here is going to be this NV003_001, the primary healthcare physicians rate per 100,000 population. You don't need to remember that, but just so you know, when we get to that part, that's what we're actually going to be looking at. So I've switched back to our Google Colab notebook here. If you are familiar with different versions of Python notebooks, then this probably looks pretty familiar. If not, let me just explain a little bit about this interface. So this is going to allow us to run Python within the web browser. It's really handy because I'm going to be using some different libraries that typically, if you were working on this notebook locally, you would need to install on your machine. But since everybody's machines are different, I found that in a workshop setting like this, it's best to provide a whole all-inclusive solution. So I suggest if you are going to follow along with me, please do use the Google Colab notebook because we'll be able to quickly install the packages that we need. If you run using your local machine, then you may not have some of the packages that we're using. And so you might run into some errors and you would need to install those packages on your local machine. This notebook file is a combination of text and then also these different code blocks. To run the code block, you can just click the little play icon here, or you can also hit Control Enter. That will run the code as well. And we'll start running code in here in a little bit. I'm just going to switch back to my slides because I do want to talk a little bit more about Python in general. Okay. So when you install Python on your machine, it comes in with a variety of built-in items. There's built-in classes, which are kind of like the building blocks of what you're going to be working with in Python. There's built-in modules, which are basically libraries that give access to various functionality within Python. And then there's built-in functions that perform certain tasks. When we look at the built-in classes, examples of these are strings, which is like text, integers, a list, a tuple, which is like a list, or a dictionary, which is a series of key value pairs. All of these classes are going to have built-in properties, which are characteristics about the class or object. And they're also going to have, some of them have methods, which are built-in functions related to the class. Note that these lists that I provided here are just examples. They're not fully inclusive lists. So also within this version of Python, you have your classes, modules, and functions like I just described, but then you can also install from using the internet or a repository, you can install third-party libraries, which are going to extend the base functionality of Python. These third-party libraries are also going to have their own modules, classes, and functions within them. Examples of third-party libraries are the Pandas library, which is really popular for data cleaning and data science. GeoPandas, which is the primary geospatial library we're going to be working with today. NumPy, which is again a data science library. And I mentioned before ArcPy, which is an API that gives you access to all of the ArcGIS Pro data, tools, and functionality. So keep in mind, you have to install these separately on your machine. They're not going to come with your Python installation. On your computer, you can have multiple versions of Python installed. So everything I just talked about can be duplicated again and again based on the number of versions you have on your machine. Some applications are going to install Python along with that application, but you can also install Python separately as well. So imagine this is your computer. You could easily have a Python 2 version, which is an older legacy version of Python. And then you could have a couple of different Python 3 versions. Python 3 is the newest group of versions of Python. So this is just to let you know that you can have multiple versions of Python on one machine. How you access them is usually based on what you prefer to work with. So you could have an integrated development environment, or IDE, which allows you to write Python scripts and run all the code all at once. You could have a Python notebook, just kind of like we're using today. You could also interact with Python through various application interfaces. Sometimes they provide you an interface to interact with their Python version. Just a little tiny, very quick syntax lesson here. So when we're talking about the properties of a class, typically those appear as the class name dot property. And that can usually be something that you read out if you want information about that property, or it can also be write or changeable if you want to change the value of that property. An example of this is, say in GeoPandas, we have the data frame class dot shape. That's going to return the number of rows and columns in the data table for that data frame. A method associated with a class usually occurs like this second line here. In this box, you have the class name followed by a dot and then the method name. And then usually you have an open close paren that can either have 0 or more parameters. This particular example has 2 parameters, the replace function, which is associated with the string class. And the parameters here within the open close parens are going to be the string that you want to look for, and then the replacement string that you want to replace it with. And then finally, when we're talking about a function, those are usually associated with the actual library or module. So the syntax is going to be the library or module name dot the name of the function, and then again, 0 or more parameters. So in this example, we have the read CSV function, which is part of the pandas library. So we're going to have pandas dot read CSV, and then 1 parameter, which is the name of the file. Intro on spatial data. So the title of this workshop, Working with Spatial Data. What am I talking about when I'm talking about spatial data? Well, typically when we're talking about spatial data, we have a data set that's going to, the data is going to have a location, information about the location, and then typically it has some kind of spatial reference, which we'll talk about here in a second. Here is an example of vector data, spatial data. And when I say vector, I mean points, lines, or polygons. Typically, when we're working with shape files, we're working with points, lines, and polygons. So that's an example of this. We have our polygons, which this polygon example is showing us polygons for various zip codes in the St. Louis area. And then underlying those polygons, we have a data table that has information about each one of these polygons. So each one of these polygons has a record in the underlying data table that has information about this polygon or this feature. So then another type of spatial data we have is called raster data. And raster is made up of a grid of continuous cells, and each one of those cells has different values in it. So we're not going to be looking at raster data specifically here in this workshop. We're going to be looking at vector data primarily. But just so you know, there is another data type called raster. These values could mean anything. They could mean the elevation at this particular area. They could represent a specific land cover or land use type. They could also represent the amount of air pollution in the air, and it's going to essentially cover the entire spatial surface that the grid covers. Okay, so in this notebook, if you click on the upper left-hand icon, table of contents, you're going to see kind of the headings that we're going to be talking about today. You can click on any one of them to jump to that particular section. This find and replace is self-explanatory. This variables list, whenever we start creating variables with our Python code, all of the variables are going to be showing up here. And then we also have these this file icon. So what we're going to do now is we're going to take those workshop data files that we downloaded to our local machine, and we're going to upload them to this Python environment so we can use them in our script. So to do that, I'm going to click on this upload icon here. I'm going to navigate to my downloads folder where I saved all of that data. I'm going to highlight or select all of the files. Actually, you know what? You don't need to do, you can upload this text file. You don't need to, but that's just kind of an FYI. It's not going to hurt anything if you download it though, or upload it. And then I'm going to click open. It's going to give me a reminder that all these updated files are going to get deleted when this runtime is recycled. So basically, when we stop using this notebook, all these files are going to go away. So this is kind of just a temporary work environment for this particular workshop. After all these files get uploaded, then we can see them here in our left-hand menu. Just to round out our little tour of the notebook environment here, we've got a little code snippet helper where you can search for different code snippets. I'm just going to close that because we're not going to use that today. This commands window is pretty helpful, especially when you're working with a notebook. It often will print things out. And so I'm just going to go ahead and click clear all outputs just in case when I was running this before, I left some outputs hanging out there. So that's going to clear all of those. And then also there's like a little collab premium tab there. So that rounds out our interface. So now I'm going to close our window so we can have the maximum real estate for our code. All right, so finally actually getting to some material here. So what we're gonna do is we're going to install and import our Python packages. We're gonna look at accessing spatial data, or essentially reading data into our script. We're going to assign an appropriate spatial reference. We're going to create new spatial data from our table of addresses. We're going to create buffer polygons around those points. We're going to do a spatial selection or isolating features based on their location. We're going to do a tabular join, which is joining a separate data table to a spatial layer. We're going to do a spatial join, which is joining two spatial layers based on their spatial location. And then we're going to, of course, plot all of the results of the above so we can see actually what's going on. So item number one, load data files into the notebook. We already did that, so hopefully you're good to go there. If you're not, again, please do speak up and we can make sure that everybody's on the same page. Just as an aside, besides opening local files, you can also access files on your own Google Drive by importing the Google Colab library. And if you look all the way down at the end of the workshop, item number 12 here gives you the code on how you can access those files from your Google Drive. Keep in mind, it does mean you're going to be giving this notebook access to all of your Google Drive files. So just keep that in mind if you decide to do that in the future. Next up, we're going to need to install some of these packages. So the Google Colab environment does have a lot of the different packages we're going to be using, but there are a few that we need to install. So we're going to be using pip, which is a package manager for Python, to install those. So I'm going to run this little code snippet here just by pressing on the play button. And you can see it's going to go out to various websites. It's going to download files and it's going to install them and give us some output notices here. Okay. And this is going to keep going, keep going, keep going. Here, see, we have installed the Census Geocode package. And if I scroll back up, I can see I have a little green check mark here that means that this code snippet ran successfully. Just to kind of clean up our space a little bit, I'm going to right click in this cell and I'm going to click clear output. That's just going to have all that printed out information just go away. It doesn't delete anything. It just doesn't show it on the screen anymore. Then we're going to run this next code snippet, which is going to install all of these packages, or excuse me, not install them, but import them into the script and make all of the functionality available for our Python code. So I'm going to click this to run. And as that's running, I'm going to just go through a few of these libraries here. So Pandas, I mentioned before, that is a library for data cleaning and data science. PyGeos and RTree are both dependencies for certain functionality for GeoPandas. We need to install PyGeos and RTree in order to do our spatial join, which we're going to do a little bit later. GeoPandas is the primary spatial data library we're going to be working with. It's an open source library and it's used a lot in various open source environments and open source work teams. The Census Geocode library is a open source geocoding reference service, which we're going to talk about when we get to that section a little bit later on. And then the Matplotlib library is what's going to help us plot the spatial data on our notebook here. Next up, we're going to set our input variables. So all of these variables here are given values that correspond to file names that we uploaded to our file section here. So typically, whenever I'm writing code, I like to put all of these reference variables right at the start. So then that way, if I change the name of any of these files or I want to bring a different file in, I don't have to hunt through the whole script to find my file name because it's right here marked as a variable. So we've got county file, hospital file, those are our shape files. We've got our health centers file, which is the first list of addresses. And then we have an alt file, which is a couple alternate addresses that we're going to be using for geocoding. And then we have our health data file. So I'm going to click the play button to import these variables. Now that we've imported some variables or specified some variables, if I look at my variables list here, I can see that these variables are now showing up in the list. It tells me what data type they are, and it tells me how many characters they are as well. All right, so now we're going to talk about coordinate systems. So coordinate systems are a critical part of spatial data. If you've ever worked with spatial data before and you've brought in a couple of different layers into a GIS and they're not quite showing up where they should be, chances are you have some kind of issue with your coordinate reference system. So what is a spatial reference or a coordinate reference system? Let's check that out. Okay, so we are all probably familiar with the fact that the Earth is a sphere-like object. So when we're talking about places on the Earth, we usually refer to their locations as locations on a sphere or a sphere-like object. And when we have a geographic coordinate system, that is the system that specifies what location we're placing a particular point at. When we take that sphere and we flatten it down onto a flat map, a piece of paper, or even our computer screen, there's going to be some kind of stretching, pulling, distortion. And so there are a series of projected coordinate systems that help translate the locations to go from the spherical object to a flat plane. So imagine you have an orange, and that orange is nice and round. You peel the orange and then you flatten the orange peels down on a table. There's going to be gaps, there's going to be stretching and bulging in places, and all of that is, you can imagine, causes distortion for locations on that orange peel. So that's kind of how you can think of geographic coordinate systems and projected coordinate systems. Projected coordinate systems are going to help minimize that stretching and bulging that flattening a round object onto a flat plane is going to do. There's about, I don't know, 1 million different projected coordinate systems. And the coordinate system that you choose should be appropriate for your study area. All right. So this could easily take up a couple of weeks of instruction in a standard GIS class. So I'm just going to kind of stop it there. But the coordinate system, the projected coordinate system that we're going to be using when we bring in our latitude, longitude values from the georeferencing output is going to be the WGS 1984 coordinate system, which is a really common geographic coordinate system for working with world locations. And then when we project that into a more appropriate coordinate system, we're going to be using the Universal Transverse Mercator, or UTM, zone 15 north. And so if you imagine a slice of the Earth that goes from the equator and up through Missouri and all the way up into Canada, that's the appropriate area for the UTM 15 north coordinate system. If you have any more questions about coordinate systems, I'd be happy to talk to you about that after the workshop. But for now, those are the two that we're going to use. So every single projection and coordinate system is going to have a specific code called an EPSG code. That's how we can kind of use a shorthand to refer to these projections. So the WGS 1984 projection has an EPSG code of 4326, and the UTM Zone 15 North projection has an EPSG code of 26915. All right. So what we're going to do is we're going to set this little text string EPSG colon and then the EPSG code to some variables so we can reuse them in our code. So I'm just going to run this and we'll see now I've got a couple more variables here. Our strings that represent our EPSG codes. Okay. So now finally, we're going to bring in some spatial data. So the first one we're going to bring in is our counties file, and this is a shapefile that represents all of the counties in the state of Missouri. We're going to use the GeoPandas function called read file, and then we have one parameter in this function, which is the name of the file, the zip file that we uploaded to our environment here. So I'm going to go ahead and run that code, and now let's take a look at some information about this file. So let's go ahead and print out the shape so we know the number of rows and columns in our data table. Let's check out what data type this is, and then we can also check out the coordinate system associated with the file. All right, for the data type, I'm going to be using the type function, which is just a built-in Python function that prints out the type of the object or the class. I'm going to convert that to a string so I can concatenate it with this whole string right here. And then I'm also going to use I'm going to access the CRS property of the counties variable that we brought in. And we're going to print that out by converting it to a string just in case and printing that out here. Okay, so this is telling me that the underlying data table for my counties file has 115 rows. So we've got 115 polygons in that layer, and it has 16 variables. So there's 16 pieces of information about each county that we have. The data type is a GeoPandas geodata frame. So essentially that's a data frame with spatial information associated with it. And the coordinate reference system is EPSG 4326. So that WGS 1984 geographic coordinate system. What we want to do, because again, remember the geographic coordinate system is the locations on a sphere, we want to work with the locations on our flat map plane. So we're going to convert the spatial reference for this layer to the UTM 15 North projection. In order to do that, we're going to be using the toCRS method that's associated with the geodata frame object. And so this is actually going to create a second geodata frame with the appropriate coordinate system. All right, so here is the counties data frame. We're going to run that toCRS method on it. And then it has one parameter, which is going to be which coordinate system do you want to convert it to? And this is referencing that UTM 15 North value that we set as a variable a couple of cells ago. Okay, so we're going to run that. And then again, you're probably going to get sick of me doing this, but we're going to check the data type and the coordinate system. It's that important. So you'll see that we're going to do it about 50 times during this workshop. Okay, so let's make sure the data type is a geodata frame. Great. And the coordinate system is our EPSG 26915. So we're all set. One other thing that I want to just note about coordinate reference systems is that there's a standard format that the GIS or any kind of spatial aware application is going to use to kind of interpret that coordinate system. And this standard format is called well-known text, or you'll often see it referred to as WKT. So I just wanted to show you that if you're interested, you can use the toWKT property to look at the information for a particular coordinate system. So I'm going to run this cell. It's going to print this out, and it's going to give us the name of the coordinate system, the datum associated with it, which has to do with the geographic coordinate system, the way that the locations are set on the sphere. But the important thing that I wanted to show you here is that if you look at the WKT, it gives you some clues about when is it appropriate to use this projection. So this is saying it's good to use this projection if you're in North America between 96 and 90 degrees west, onshore and offshore, and it gives you kind of a list of locations. So up in Canada, in the United States, it's good for Arkansas, Illinois, Iowa, yada, 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 and Missouri right here. Okay, so just a little snippet on how you can find out more information about these projections. I'm going to clear this output here just because it's really long. And finally, we're actually going to look at our spatial data here. So this is where our matplotlib library comes into place. The first thing we're going to do is we're just going to set some variables on the figure size we're going to use. We're going to use the plot function associated with the geodata frame. We're saying for the axis or the plot that I want you to add this to, it's called AIX, which we created here. I want you to put all the polygons in a gray color with a white outline is what that's saying here. The tight layout just kind of tightens the layout a little bit. And then we can either save the figure to a PNG or an external image, or we can just show it right here in the notebook. So I'm going to click that run, and this gives us essentially our counties file plotted, shown on the map. And if I look over on my files list, I can see I've got this counties-based PNG. If I double click on that, that also shows me that this has exported into a file. The FIG, yep. So this is essentially just setting up the plot. So we're going to run this each time, and it's going to give us a base of the plot. The plot is going to be, the ax is going to be how we refer to that particular plot later on. So we want to add our spatial layers to that plot. And then the fig is just saying we want like this size of figure. Okay, so so these things here are not necessarily spatial. They're all associated with the matplotlib library. So you're going to see that whether you're using spatial data or if you're plotting a line graph or something like that, it would be the same kind of setup here. And forgive me for the folks on Zoom, the question was just explaining a little bit more about this first line, the matplotlib plot that we set up. Cool. So our plot looks pretty good. Again, to save a little bit of screen space here, I'm just going to right click and I'm going to say clear output just to kind of get that off of our screen. Okay, next up, we're going to do some geocoding. So let's take a look and see what we're talking about here when we're talking about geocoding. So geocoding is the process of taking a list of addresses, most of the time, taking a list of addresses and then converting them to spatial points. So the important thing, the important components that you need when you set out to do some geocoding is, first, you need a list of addresses. Usually you want them separated kind of like this sample table here, where you've got an address field, a city, a state, and a zip code, sometimes a country if you're doing international work. Then you need some kind of reference information for the GIS to geocode against. And that reference information can come in a couple of different ways. Historically, we've used file-based reference information, or also called locators, where the GIS takes in your list of addresses, it looks at the reference information, and then it finds a way to generally place those points based on where either an exact address or generally where it thinks that point should be placed. But now we have even more reference information options, because a lot of reference information is now available as a web service, which you can access through the internet. So my arrow doesn't quite look right here, but imagine that we're running this address list through a web-based locator and getting a similar output, these points on a map. So the reference information that you use is really going to be based on what's available to you. There's some reference information that you can pay money to access. There's also open source options. And so we're going to be using an open source option today. We're going to be using a web service that is available through the US Census. So that's where that Census Geocode library that we installed, that's where that comes into play. So the Census Geocoder, it's a REST service, and it's going to return us a latitude and longitude value for a single address. And you can do a batch of up to 10,000 records at a time with this geocoder. All right, so then we're going to take the latitude and longitude pairs, and we're going to use them to create some spatial data. Okay, so first up, we're going to perform the geocoding. We're going to use the address batch function that's part of the Census Geocode package. What it's going to do is it's going to read in the CSV file. And keep in mind, the CSV does have to be formatted in a specific way. The census does put out a sample file here, so you can make sure that your addresses are formatted correctly. But what it does is it accesses that data file, it goes out over the internet, it calls the geocoding service with the address information, and then the service returns information about the address, including the latitude and longitude. These are returned as a list of dictionary, well, the full file is going to be returned as a list of dictionary objects, but for each record, it returns a single dictionary. So you can pull values from that. So let's go ahead and run the geocoding operation. Now, again, if you're not running your notebook in the web browser here, you may see an error telling you that you don't have the Census Geocode library installed. So that's why I recommend working with me here in the web browser. But that didn't take very long. We only had 10 or 11 records, so it was pretty fast. And now we're going to take a look at the output. So what kind of output did we get? So I'm just going to print out the type here, and it tells me that it's a list. Okay, so what I'm going to do is I'm going to use a for loop to loop through each item in the list, and we're going to print out each item so we can kind of get a feel of what our result looks like. So we're going to print out each item in the list, and then I just put a bunch of asterisks here just to divide out the records, just so it's easier to see. So I'm going to run that. Now I can see that each item here is a dictionary, and then I can see a series of key value pairs that gives me information about that particular address. Another way to look at it here, if I go ahead and clear my output from that, is we can take that result and we can load it directly into a Pandas geo, not a geodata frame, but a Pandas regular data frame. So we can see the output as a table, which is a little bit easier to see. So let's check that out. Okay, so now we can see this as a table. We've got an ID, we have the address that came in, here's the address that was matched. And then most importantly, here at the end, we've got our latitude and our longitude values that we're going to use. It also returns the FIPS code for whatever state it happens to be in. And so just a little bit of helpful information. So far, it looks pretty good. Of my 10, 11 records, it looks like only 2 weren't found. So not bad. So let's see what we can do about that. I'm going to go ahead and just remove this table for now. All right. So the Census Geocode service does perform a limited amount of approximations. Some other geocoding services, often the ones that you pay money to access, will do a little bit better job at giving you potential matched addresses, so you don't have to do a whole lot of work to match them back up. If we look at the match type column, this is how we know if something was matched exactly or matched, like kind of fuzzy matched, or not matched at all. We can see we have some non-exact matches, which are probably going to get us close enough for our purposes, but depending on your project and your time and your budget, you may want to invest some time in rematching them to get them exactly perfect. Okay. So we're just going to take a look and see which records didn't come out at all. Like we got 0 information about these records. What I'm going to do is I'm going to create a new variable called unmatched. And what this is going to do is it's going to take all of the health centers that from the data frame, so the health centers data frame here, and it's going to isolate any records where the match field here is equal to false. All right, so these square brackets, the first set of square brackets essentially is telling us that we're going to isolate certain records. That's kind of a selection operation. And then these square brackets here are specifying the column that we're going to look at to isolate those records. After I create the unmatched geodata or data frame, I'm just going to print that out so I can see what records we have unmatched. Okay, so there's just those 2 records where match equals false, and they're shown here. Now, one other thing about this line of code right here, if you're not familiar with the various conditional operators that you can use in Python, this double equals sign here is how we tell Python that we want to find equivalency. The reason why we need to use two equal signs is because we're already using a single equal sign to assign our variables. So we need to make sure that we differentiate between assigning our variable and looking for equivalency here. So that's why we're using two equal signs. All right, so like I mentioned, the amount of work that you want to spend on researching and correcting your geocoding results really depends on your needs or your project needs. So since this is a small data set and we're in a very controlled environment here, I went ahead and I looked up those unmatched records and I found some alternate addresses that are generally close to the original address. This isn't necessarily like a best practice, but in our situation here, our study area is the entire state of Missouri. So it's really not going to matter to us a whole lot if a point for a certain address is actually on the building or maybe the building next door or across the street. So you kind of want to keep that in mind. All the precision of your study area, the size of it, how many records you have, because if you're geocoding 5 million records, you may not have a lot of time to go back and fix all of the ones that didn't get matched. Typically, we want to see somewhere in the like 85% and over match rate. That's kind of generally, I would say, an acceptable result. But again, it's all going to depend on your project. Okay. So I'm going to go ahead and run that address batch function again, this time on the alternate health centers file, which just has 2 addresses in it. So I'm going to run that, and then we'll take a look at the output as a data frame here. All right, so it went out, it found those alternate addresses, and it's given me the lat long that we need. So now what we can do is go ahead and combine the results. So the first thing I'm going to do is I'm going to take our original data frame and I'm going to get rid of those unmatched records. So here I'm using the drop method associated with our data frame. And for my parameter, I'm saying drop all the records where the match field equals false. And then I'm also using this in place method to not create a separate data frame, but just do it all within the same data frame. All right. This little index here is just saying, find all the records where match equals false, get their index and drop those. By index, I mean the unique identifier for every single row. It's kind of like a built-in function of the data frame. We can take a look at that here. Okay, this is what I'm talking about when I'm talking about the index here. This is the index, which is how Pandas keeps track of each of the records. So now I can see that all of my records are the matched ones. So that's good. That's our first step on combining them. Now I'm going to combine the 2 data frames using the concat function in Pandas. So first I create a list of the data frames to be combined. All right, so that's just a list here. And there's 2 elements in the list. There's our original data frame and our alternate data frame. Then here's where I'm calling the concat function and creating a new variable to hold that new data frame. It's going to be called health centers all DF. I'm doing a reset of that index just so, you know, if we're removing records and then putting records in, it's just going to readjust that index so that each record has its own sequential unique index. And then finally, I'm going to display them all. Okay, so now I've got my records here, and they all have our latitudes and longitudes. And they're all in a single data frame. So we're looking good. I'm just going to clear all that output. And then finally, we're going to take those latitude and longitudes and we're going to transform them into spatial points. So I talked about the different kinds of geocoding locator data. Some geocoding tools are going to go ahead and create that spatial data for you and give you an output shapefile. The Census Geocoder is just going to give you a table back with that latitude and longitude, and you need to convert those into a spatial file. So the GeoPandas library has a function that will accomplish this kind of automatically. It's just going to be our regular geodata frame creation or instantiation method here. So we're going to create a new Health Centers geodata frame. It's going to be a GeoPandas geodata frame. And then here are the parameters that we're working with. The input data frame is our Health Centers all data frame. We need to say, okay, what are the geometries? What are the shapes of this spatial data? So we're going to separate out those latitudes and longitudes. And we're going to say, first, we're going to say, okay, GeoPandas, use your points from X, Y, and you're going to create a point at this longitude and this latitude. And you're going to set that as the geometry for these points. And then finally, we're going to say, initially for your spatial reference, I want you to use the WGS 1984 or EPSG code 4326 spatial reference for these latitudes and longitudes. All right, so I ran that. It ran fine without any errors. And again, we're going to check our data type and our coordinate system. All right, so our data type is a geodata frame. Great, that's what we want to see. And then our appropriate coordinate system got applied there. All right, this is fine and this is all good, but remember, we're working in the state of Missouri here, so we want to make sure that our points are in an appropriate coordinate reference system. Also, our polygons are in our UTM 15 North coordinate system. So we want to convert these points to the same coordinate system. So when we display them, they're going to display all in the right spot, which is on top of each other. So again, we're going to use our 2CRS method here. Our parameter is going to be this zone 15 North EPSG code. And then, of course, we're going to check our data type and we're going to check our coordinate system. Our new data frame is going to be called Health Centers UTM 15 North. All right, so that's a geodata frame and it has the appropriate spatial reference. So finally, we're going to plot these. Okay, we're going to start with our original figure and access parameters here. First, we're going to plot our counties just the way we did previously, but next we're going to drop our new health centers data on top. The marker size, just the size of the point, is going to be 10. And then we're going to print them or have them be in a red color. We'll also go ahead and save this out to a file as well as show it on our screen. Okay. So now we've got our Missouri polygons with some red dots that represent our health centers. All right, so we're going to be kind of building up some layers here. Okay, so I'm going to clear our output here. I could check the file, the image file. Here's that image file we just created. So that looks pretty good also. Okay, and we're ready to go on to the next thing. So now we're going to move into not just bringing data in and you know, the basic creation of the data. We're going to actually do some spatial analysis here. So we've got a couple of spatial analysis tasks we're going to cover. We're going to do some buffers, which is a really common spatial analysis task. And then we're also going to do a spatial selection. So a buffer, you may already be familiar, but we're just going to take a particular feature. It could be a polygon, a line, or a point. And what it does is it calculates a a separate polygon that has a diameter of whatever you specify, so a distance from that feature, and it will create a second feature that is around the original feature. So we're going to do a buffer on the health center points, and the coordinate reference system of the points right now is our UTM 15 North. So all of the coordinate reference systems have a particular linear unit associated with them. Often it's going to be feet or meters. It's pretty typical. For the UTM 15 North projection, that linear unit is meters. And when we printed out that WKT string, the linear unit was specified there. So if you were ever curious about what the linear unit for a coordinate reference system is, you can check out the WKT and it will tell you. But UTM 15 North is meters. So if we wanted to take our health center points and we wanted to create a buffer of 10 miles around each one of those health centers, then what we need to do is just convert miles to meters. So about a little over 16,000 meters is equivalent to 10 miles. So we're going to take that number, 16,000. Oh, and I see I have a little typo here. I can just fix that right here. That's the beauty of our little web-based thing. There we go. And so we're going to use the distance parameter of the buffer function, and we're going to insert a value of 16,000. Oh, and that didn't change. Okay, well, whatever. 16,094 meters. Okay, so here is that buffer function, and the buffer function, or excuse me, it's a method associated with the geodata frame. So we're going to say geodata frame name dot buffer function. And then in the parentheses, we have one parameter, that's the distance parameter. And we're going to insert our number of meters in there. So if I run that, we're going to have a new, what do we have? We have a new geoseries here. And the coordinate reference system is 26195. So the difference here between the geodata frame and the geoseries is that the geoseries just has essentially one column of information about each feature. In this case, our information that we have is just the shape. We don't have the name of the health center. We don't know anything else about this particular shape except for it's right here in this location. Okay, so that's fine. We can interact with the geoseries pretty much in the same way as we can with the geodata frame. So now we're going to plot those buffer polygons. So this might be starting to look familiar here. We're setting up our plot. We're adding our counties. And then right above our counties, we're going to add our buffer polygons that we just created. We're going to color those purple with a white outline. And then on top of those buffer polygons, we're going to place the health center points. If we went the other way, then the buffers would be covering the points. And so our layers are going to be drawing from the top down. So we want to make sure that we plot the health centers on top of the buffer polygons. So again, we'll save that out to an image if we want, but we'll also show it on our notebook file. Okay, so now we're seeing our red health center points and then our 10-mile buffers around each point. Okay. Any questions on that particular spatial analysis step, the buffers? Then we're going to go to another spatial analysis step, and that is spatial selection. So what we're going to do here is we're going to isolate features based on their relationship with another layer. So we're going to use our health centers buffers, and then we're also going to use a new file, which is all the hospitals in Missouri. So first we're going to read in this hospital file using our read file function that's associated with GeoPandas that we ran before. That's going to give us a new geodata frame called hospitals GDF. got to check that data type and that coordinate system. Okay, we're showing a geodata frame, and also it's come in as the WGS 1984 coordinate system. So what are we going to do? We're going to convert that to our UTM 15 North coordinate system, so all of the data aligns with our existing data that we're using. So we'll call that 2CRS method again, that's associated with the geodata frame. The parameter is going to be that UTM 15 North coordinate reference system, and our output variable is going to be hospitals UTM 15N. We run that and we check. We still have a geodata frame, great, and our new coordinate reference system is the EPSG 26915. Awesome, okay. So now let's check those hospitals, make sure they're showing up in the right spot. So again, we're going to create our plot. We're going to plot our counties. We're going to go ahead and create those plot those buffers as well. And then we're going to plot our health centers on top of the buffers. And then also on top of the buffers, we're going to plot our hospitals. Our hospitals are going to have just a little like O type marker or a circular marker. And these are going to be black. And they're also going to be pretty small. They're going to be size 5. All right, we've also saved this out to a new PNG, or we can show it on our workbook. All right, so now we've got our state of Missouri, we've got our buffers, we've got our red health centers here, and we've got a variety of little black dots that represent the locations of hospitals in the state. All right, so now what we want to do is we want to isolate all of those hospitals that are within 10 miles of our Planned Parenthood health centers. So in order to do that, we're going to check and see which hospitals are within our 10-mile buffers. All right, so we're selecting features based on their spatial location. That's our spatial selection. I'm going to get rid of our map here for the moment. Okay, and so first we need to do just a little bit of work with the polygons. So we want to essentially isolate those polygons, and we want to convert them into a single feature. So we can find all of the hospital points that are within this one feature. This particular feature is going to be called a multi-part polygon because it's going to be read as a single feature, but it has multiple parts to it that may not overlap spatially. In order to do that, we're going to use this unary union function. And that's going to combine our polygons into a single polygon. So let's check that out. We'll use that function or that method. It doesn't require any parameters, and it's just going to be saving out that one feature. It's going to be called Health Centers Buffer Poly. And we'll check out the data type on that. Okay. So when we check out this data type, it looks a little bit different from what we've seen before. We have a single multi-part polygon here, and we can also see that it's not necessarily associated with GeoPandas. It's associated with this library called Shapely. Shapely is another spatial library that happens to be a dependency of GeoPandas. So that means that GeoPandas cannot run unless Shapely is installed. So when you install GeoPandas on your machine, it's also going to go ahead and install Shapely as well because it's built on top of that particular library. That's pretty common for spatial libraries to have things called dependencies that are other libraries that are necessary for a particular library to run. So Shapely just happens to be a dependency of GeoPandas. We can still work with this with our GeoPandas functionality. So to do our spatial selection, we're going to use the within method. Okay, so we're going to create a new variable called hospitals close to health centers. And to do that, we're going to be again isolating some features here using our square brackets. This is our feature isolation syntax. And then what features are we going to isolate? We're going to isolate all of the hospitals that are within the health center's buffer polygons. And so once we do that, we're going to isolate those from the main group of hospitals, and we're going to have a subset of hospitals that are close to the health centers or within 10 miles of the health centers. So let's run that. Then we're going to check out our data type and our reference system. So this has then taken that original geodata frame and it's created a new geodata frame that's only those health centers. And it does have the EPSG code of 26915. Now that we've isolated those, let's plot those in a way that we can see those hospitals highlighted. We're going to do that like this. We're going to set up our plot. We're going to plot our counties. We're going to plot our buffers in purple. We're going to plot our health centers in red. And we're going to also plot our hospitals in black. But in between those two, we're going to plot our hospitals close to health centers geodata frame. And we're going to plot those in yellow. And we're going to make the marker size quite a bit bigger than the standard hospital marker size so that those hospitals essentially show up as highlighted in our image. Let's take a look and see what that looks like. Okay, so looking at our plot, we can see we have our standard hospitals that are not within 10 miles of a health center. They're still showing up in black. The hospitals within 10 miles have the appearance of this little yellow highlighting, which is essentially that second geodata frame showing underneath our original geodata frame. So it gives the illusion of like a highlighted record. We could certainly show those in some other symbol as well, but I just wanted to show you those are the same hospital points, just with a symbology that's going to make those pop out a little bit more for us. Okay. Let's close this. And then I'll take a pause for any questions or comments before we go on to our tabular join. So there's really nothing special about a tabular join. We could really just call it a join. That's what it is. But the reason why I like to specify tabular join is because we're going to take a spatial data layer. We're going to take that underlying data table and we're going to join a standard data table to the underlying data table. So I like to use tabular join just to specify the fact that we're joining two tables together. If this was a standard data cleaning workshop, then I'd just call this a join. And we'd talk about inner joins and outer joins and all that kind of stuff. But for now, what we're going to do is we're just going to join the underlying data table with an external table based on some similar values in the tables. Let's just take a quick look to see what that's going to look like. Okay, so remember I told you about vector data where each polygon has an associated record in the underlying table. So that's this attribute table that we're seeing here in the middle of this image. We do a join on our standalone table for records that match values. So this spatial layer is for zip codes, and we've got a zip code column in the attribute table. Then we have our standalone table, which is some additional data, and each of these records also has a zip code value. So we can match these zip code values, and then the table gets joined to the spatial layer. And then we can use the data from the standalone table to visualize in our spatial layer. So the first thing we're going to do is we're going to read in that health data file. It has all of the records by county. So we know that each record is a county. So those should match up pretty well with our county's polygons. So let's read that in. And then we're going to use the head method here just to take a look at the first few records in this table so we can check out what they look like. All right, so we've got a GeoFIPS here. If you're not familiar with the concept of a FIPS code, a FIPS code is a unique identifier or a unique code for geographic entities. So each state has a unique FIPS code. For Missouri, our FIPS code is 29. Each county within a state is going to have a unique FIPS code. So St. Louis City has a unique FIPS code of 510 within the state of Missouri. St. Louis County's unique FIPS code is 189. So this is a way to provide a unique identifier for different geographic entities. It also is really helpful for matching up records. So we've got GeoFIPS here, we've got a bunch of other stuff, and then here's where all of those SE columns start. It's not going to show us all of them because there's way too many to show. So maybe we could pare this down a little bit so that we can see all of those columns, or at least just, you know, take out the ones that we want. We don't need all of them. So I'm going to clear this output just for a sec. And what we're going to do here is we're going to loop through all of the columns and we're going to print them out just so I can get a big list of all the columns in this table. I can do that by accessing the columns property of the data frame. So what I'm going to do is I'm just going to take all the columns and I'm going to list them out in order. Okay, so here's all of these columns. There's quite a few of them. So all we're really interested in is the column that I mentioned before, the primary care physicians, or PCP, rate per 100,000 population. You could choose any of those attributes, but this is just one that I chose to visualize. Also, there was quite a bit of like missing data in some of the records. And so this one had a lot more records filled out. And so it's going to look better when we plot those on the map. So what we're going to do is we're going to create a new list, and I'm going to call this keep calls or keep columns. And this is just going to be all the columns from that data frame that I want to keep. So we're going to keep our GeoFIPS or our FIPS code. We're going to keep the name of the column. We're going to keep the state and the name of the county. And then of course, we're going to keep that actual data, that piece of data, that PCP rate. So we're going to run that. So we have this list of strings, and then we're going to use that list when we read in the file again. So this is kind of handy if you have a huge spreadsheet with a lot of columns in it. You don't want to bring in all of those columns. You can isolate just a handful of columns to bring in to keep your data a little bit more manageable. So we're going to use that read CSV function again on our health counties data file. But this time we're going to specify using the use calls parameter that we only want to read in the columns in our keep calls list. So we'll read those in. Again, let's check out the first few records of our table using the head method. Now we can see our table's much more manageable and easier to deal with because we only have those records that we want. Okay. Another thing that I like to do when I am examining a data table is I like to look at all the unique values in a particular column. It tells me if I have any cleaning that I need to do, like if there's NA values and so on and so forth. So if I just use the unique method here on our data frame, I'm saying take our health data frame, isolate this column and give me all of the unique values within that column. It gives me essentially an array that has a bunch of values in it. And we're not printing out all the values, but if you wanted to, you could easily print out all those values in a loop to see what values you might need to clean up a little bit. For now, we're just going to take this column as is. I also want to take a look at the last records in the table just to see, what we've got going on. And I can see that here is where the fact that this table has all of the counties in the US is really showing here. So this is some US territories. So what we want to do is we want to isolate only the records in this table for Missouri. And I mentioned before that the FIPS code for the state of Missouri is 29. So we're going to take advantage of that and we're going to isolate our Missouri records. So I'm going to create a new data frame here. I'm going to call this one Health Data Mo. And to do this, I'm going to use my isolation square brackets here that we've used a few times. So this is saying, okay, in this data frame here, I want you to isolate all the records that match a certain criteria. That criteria here is where the geostate value is equal to 29. So if I get that new data frame, I look at my data frame, and sure enough, for geostate, all of those are 29. I've got my FIPS code here, which also starts at 29. And so I have my data table that's essentially ready to be joined to my Polygon shapefile or my Polygon geodata frame. However, there's a couple other things that we need to do before we're ready to do this. Let's just note that for GeoFIPS, we have the 29 is in front of each of our state or each of our county FIPS code, making a very specific GeoFIPS code. So they're all starting with 29. All right, just keep that in mind. When we get set to do our join, we need to make sure that not only our values match, but also the data types of the two columns we're going to use to match, those also have to match. So if you're going to match on integers, both columns have to be integers. If you're going to match on strings, both columns have to be strings. So let's check out what Python is interpreting these data types as. To do this, we can take a look at the dtypes property of our data frames. So if I look at the dtypes of our health data, it's showing me that the GeoFIPS is coming in as an integer. Okay, let's look at the data types of our counties. All right, so for our counties, we've got a counties FIP that's coming in as an object. An object means it's a mixed data type. So Python is saying, you know, this has something that looks like both numbers or characters or whatever. Most of the time, it looks mostly just like characters, but it comes in this object data type. All right, let's take a look at that county FIPS code. I want to refresh my memory on what that looks like. Okay, so county FIPS in our Polygon data has just a 3-digit county FIPS code that's coming in just the county FIPS code. So what we want to do to make sure that these match is we want to make sure that that our county FIPS code has that 29 in front of it, so it matches the values that are coming in our separate data table in that GeoFIPS column. Okay, let me get rid of this. Okay, so it might be a little bit easier to see what we're dealing with here if we use our sort values method, which is where we're just going to sort in ascending order on our county FIPS attribute or column here. And we're going to set the in place parameter to be true so that it doesn't create a new data frame. It just sorts it all in place. All right, so if we look at that again, we can see, okay, now it's sorted by county FIPS. So we have 1, 3, 5, those are all showing up in order. I wanted to do this mostly because I wanted to check that these leading zeros were coming in, because the county FIPS codes sometimes do have leading zeros, to make sure that every single FIPS code is a 3-character code. All right, so I mentioned that what we need to do is we need to add the state FIPS code of 29 to the beginning of these FIPS codes so that these values match up. So what we're going to do is we're going to create a new column in our data frame. Now here's a little bit newer way of dealing with the square brackets. We haven't seen this yet. This says the square brackets in this instance mean I want you to create a new column in our data frame. So we're going to take our counties data frame. We're going to create a new column called GeoFIPS, which just happens to be the same name as the column in our standalone table. And the values that are going to be populated in that column are going to be a string 29. I'm converting it to a string here because I want to make sure that the string gets concatenated to the existing record here. And so what I'm going to do is I'm going to concatenate 29 with the existing county FIPS code. I'm going to do that first. You can see that that's in parentheses here. And then after I do that, I'm going to use the as type method to convert that to an integer. The reason why I'm doing that is because remember when we checked the data types of our standalone table, that GeoFIPS column was coming in as an integer. So we want to make sure that those are the same data type. So let's go ahead and do that. And now we can check out the first few records and we can see, will this show me? Oh my goodness, there we go. That we've got our GeoFIPS new field and it has all of the FIPS codes with the 29 in front of it. That's great. That's setting us up really nicely to do this tabular join on the GeoFIPS column. Okay. All right, so now we can finally do that join and we're going to use the merge function that is part of Pandas. There's a couple of parameters that are important here in this merge function. So the results of our merge, are going to be called counties with health, and we're using the Pandas merge function on our counties data frame and our health data frame. What column are we merging on? We're merging on the GeoFIPS column, which is the same in both tables. That's why I named them the same, because it's a lot easier to join if you have columns that have the same names. Not entirely necessary, but just for ease of use here. And then how are we going to join this? We're going to use a left join. All right, now really quickly, this is going to link us back to a different presentation that I did, but I just want to show the different join types real quick. So say you have two tables here. We have table A and table B. The left join is going to have all the records in table A and only the records in table B that match. All right. A right join is going to have all the records in table A and only the records from table, or excuse me, all the records from table B and only the records from table A that match. Inner join is where only the records from both tables that match. And outer join is all of the records, regardless of if they match or not. So what that looks like here, doing a left join on these two tables, we can see that table B has some null records here because there was a record in table A that did not match table B. That's a left join, so that's the one we're going to do. A right join here, let me just make this a little bit bigger. A right join is where all the records from table B are present and only the records from table A that matched are present, meaning that we do have some null values for this particular record. An inner join is where only the records that match appear. So we only have 3 records there. And then a full outer join, we're going to see all the records from both tables, but some records might have columns with null values because they didn't match. We matched an ID on all of these examples here. Okay, back to our workshop. Okay, so let's run our merge. And now we're going to look at just the first few values. All right, so here's the first couple of records that were in our county's polygons. And now if we scroll over, We can see now we have the additional columns that came from our second external table, along with this attribute here that represents the value that we're going to map, that PCP rate. All right, so this is great. We're looking good so far. Let's clear that. Gotta check the data type in the CRS. This is still coming in as a geodata frame here, and its EPSG code is 4326. What do we need to do to that? We need to convert it to UTM 15 North by using our T2CRS function right here. So we're gonna have this new data frame that's counties with health UTM 15 North. If we double check the data type, it's still a geodata frame, and now we have our new coordinate reference system. Okay, finally, we get to plot this after all that. Now, this is going to be a little bit different because our regular county polygons that we were plotting in gray, we're going to get rid of those and we're going to replace those with polygons that are going to be symbolized based on the value from our external table. Okay, so let's take a look and see how we do that. Here we're calling our new geodata frame. We're calling the plot function. The edge color or the outline of the polygons is going to be black. We're going to plot that on top of our existing axis plot. We're going to specify column, the column parameter, which is going to tell Python what column do I want you to look at the values of to determine the colors. So it's going to look at that column. I'm setting legend to true, so it goes ahead and it creates that legend so we can see what the colors mean. And then also, we're going to specify that if there's any missing values, I want you to go ahead and color those polygons with light gray. So that's what this missing KWDS parameter is. This is specifying what do you want to show the missing values like. Okay, all of these other lines of code we've seen before. We're gonna plot those counties, then we're gonna plot the buffers, the health centers, the hospitals, the two different types of hospitals. We're gonna plot those on top. We're going to give this plot a title, just so our audience knows what we're looking at: primary care physicians, rate per 100,000 population for Missouri counties. So let's see what that looks like. All right, so we've got a little choropleth map here. It's giving us the rate in various colors, and we can see where the rates are particularly low, meaning not the rate of primary care physicians is low based on population, and where it is a little bit higher. We can kind of see, unfortunately, St. Louis City and St. Louis County are kind of hidden there. If we wanted to, we could always run this again, and we could maybe hide our buffers by just commenting out that line. We could run that again. Our buffers are gone. So now we can see a little bit better what's happening with the various counties. And we can also see that our counties with no data are showing up in this light gray. So now we're going to move into our spatial join. So like I mentioned before, a spatial join is where you're joining two different layers based on a spatial relationship between the features. This is a really powerful tool, and it's probably one of the most common workflows that I help users with here at the library. I'm just gonna do a little graphic of what we're actually doing when we're doing a spatial join. Okay. So there's lots of different relationships you could evaluate with a spatial join, and I've listed out two of the most common ones that I see. So essentially what we're doing is we're going to be creating a new layer that has some kind of transfer of values between the two layers. So in this little example here, we've got some polygons and we've got some points also. All right, so two separate layers, our polygons and our points. One common example of a spatial join is counting and summarizing the points and values from the points within each polygon. So your output is going to be a polygon layer. So here's some unique, this is indicating a unique ID for each polygon. It's going to give you the count of the number of points within each polygon. And then say the polygon has some value associated with it. It can also give you a summary of the values of those polygons. So looking at polygon 007 here, it says that we've got one point within this polygon, and whatever column we wanted to summarize, it had a value of 19. Polygon 027 has 2 points, so we have the count of 2, and the summary of whatever attribute we're summarizing, the sum of that is 32. Okay, so that is counting points within polygons and summarizing values from the points within each polygon. Another example of a spatial join is where you can apply values from the polygon back to the points that are within the polygon. So that's the second table here. So we have point number 150, okay? The value of the polygon that that point falls within is polygon 007. And say I wanted to get the county name for each county that that polygon falls, for the county that the polygon, or excuse me, I want to get the county name, which is the polygon, for the county that the point falls within. So in a spatial join, we can retrieve that value and have a point layer that will have those values as part of the attribute table. So those are two common examples of spatial joins. There's other things you can do, but those are the two really common examples. And for our purposes here, we're going to do this first value or this first example where we're going to count the number of points within each polygon. And then each one of those points, we're going to use our hospital points. Each one of the hospital points has an attribute that's the total number of beds in that hospital. So we're going to use that value to summarize and get the total number of hospital beds in the whole county. All right, so like I said, we're going to try to calculate the number of beds in each county. So the first thing we're going to do is we're going to perform the spatial join using the S-join method associated with the geodata frame. So we're going to be taking our counties and we're going to be joining our hospitals to those counties. All right, so we're going to keep all the hospitals and then we're going to apply. So you know what, I misspoke, I apologize. We're eventually going to get to the total beds, but this output here is going to be the hospitals and then the counties that they're associated with. All right, but we'll just keep going because we want to isolate. So again, it's a lot of columns. We can't even fit them all on the same screen. So I'm just going to isolate them, isolate the columns using our little keep calls list. It's going to be a new keep calls list. And now we're just going to have these hospitals here with the county name associated with each hospital. Okay. All right. So now what we can do is we can take those counties, we can group them by the county, which we're going to use the FIPS code. And then we're going to use the sum function here to get a new table, which is going to be the sum of all of the beds per county. All right, so this table here, it's got a list of all of the county FIPS codes with the sum of the beds. Now, just kind of looking at this data just really briefly, I mentioned that the county FIPS code for St. Louis City is 510. We can see right here that the county FIPS code 510, the bed count is over 3,000. And just knowing what we know about the counties in St. Louis, the counties in Missouri, That makes sense because we know that there's a lot of hospitals in St. Louis City and they're big ones too. So they're going to have a lot of beds. All right. So now what we're going to do is we're going to merge the counties back to the county's polygon. So we're going to take this little table of our total beds. We're going to merge it back to our county's polygons using the merge function that we used before. So if we scroll down to the end of this table, we've got our total beds column now. Okay, and it looks like some may not have any, so that we've got this null value. I'm gonna get rid of that output for now. Let's check our data type. All right, so we've got our coordinate reference system and the data type is our WGS 1984. We need to convert it to our UTM 15 North, and we'll double check that. And that looks good. Geodata frame, EPSG 26915. And then finally, we can map those like in the same way that we mapped our previous ones. Okay, so in this chunk of code here, we are mapping our counties with bed counts geodata frame. We're using total beds for what we're going to match on or visualize on. And I just specified a different color ramp or color map for this just to make it look a little bit different. You can look at this documentation link, which has a little bit more information about using different color ramps. And also our missing values are going to be dark gray. So let's take a look and see what that looks like. Okay. All right. So relatively speaking, it looks like there's not a whole lot of stuff happening here. Okay. But just based on our color map, we know that the hospitals with kind of lower numbers of beds are going to appear more in the lighter color ramp. And then the color ramp is going to turn into the dark purple, depending on how many beds. So each of the counties here that have what looks to be a single hospital, you can see that they have a lower number of beds. And then the higher bed counts are going to be in the more populous counties here. So anecdotally, that makes sense. We might want to adjust the color ramp a little bit so it looks a little bit, so it's maybe a little clearer, or maybe we can divide these up a little bit more into different categories. But for now, we're just going to use this continuous legend and move forward with just some final map preparation. So, you know, if you're creating a map for a report, you may want to consider using a desktop GIS that has a little bit more robust cartographic capabilities, but there are some things that you can do within the Matplotlib library to clean up your map a little bit. So the first thing we're going to do is we're just going to remove these access lines. So I've just inserted in here this x-axis equals off. So that means that this next plot here is not going to have the access lines that the other plots had, just making it a little bit cleaner. Next, I'm noticing that the legend is extending far above and below our polygons. So we want to adjust that a little bit so that the legend is a little bit more manageable in our plot. And then also we have a lot of points and symbols here that don't have any explanation for our users. So we want to go ahead and create a legend as well. Finally, for any map, you want to make sure you include a scale bar so that the scale of the map can be quickly discerned from by the reader. So to finish this up, we're going to bring in another module from our Matplotlib library here. Okay. And in this section here, this is where we're going to be adjusting the legend size. So we've added a few more things here. These 2 lines of code. We added this divider component, which essentially gives us the control over setting different sections of our plot. And we can apply that divider and have that section be on the right side and have it be just a little bit bigger than our total polygon area. Then when we're looking at plotting the bed counts, we've added the CAX parameter here, which ties back to this divider that we've added. So we're saying, okay, put the legend in that right-hand section and make it just about 5% bigger than this element, which in this case, the element is our polygons. Let's take a look and see what that looks like. All right. So now our legend is lined up a little bit better. We've got our total hospital beds defining what the legend is showing us. So that's cool. And then finally, let's go ahead and add our legend and our scale bar. Okay, so to do that, we do need to fully install a whole nother package called Matplotlib Scale Bar. So we're going to go ahead and do that. We're going to install it using pip, and then we're going to import it into our script. Okay, so we have our little green check mark there. So that looks good. Now we're going to import a couple more modules from our Matplotlib library. This is going to help us show the different patches and lines in our legend. And then we're also going to import the scale bar module so we can add a scale bar. So we'll add those in. Here is where we're going to create a list of elements that we're going to put into our legend. So our legend is actually not directly tied to our markers on our map. We're kind of just manufacturing this legend on its own. So what we're having here is we're creating a line, but we're making the line color white so it doesn't show up on our background. And we're adding a marker to that line that's equivalent to the color that we used in our map. So for our health centers, we're using a red dot. For our hospitals, we're using a black dot. For our hospitals within 10 miles of the health center, we're going to add a black dot, but we're going to give it a yellow edge color so it kind of shows that yellow outline. And then finally, for our no data polygons, we're going to be adding a patch or a square that says, okay, no data looks like this. So this is going to be a list of elements for our legend. And I know it's a list because of these square brackets here. Okay, that's our legend list. We're going to create a scale bar element that we're going to place in the lower left. We specify that here. The scale bar is going to be associated with our polygons, so it's going to pick up the correct distance and everything. And then finally, we're going to add all this stuff to the map. So let's see what we've done here. We turn off our axis. We have our divider and our CAX that gives us the placement of the legend. We're going to add all of our layers here, which we've looked at before. Here, we are going to add a legend, and the legend is going to reference this list that we created above here. We're going to add our scale bar, all right, which is going to add that to our map in the lower left location that we specified here. And then that's it. It's going to give us a title. We're going to save it out to a new image. And finally, let's take a look. All right. So now we've got our total hospital beds and we've got our legend that shows what our points are representing. And we essentially, there's our scale bar, and we essentially have a pretty passable final map here. So thank you very much. Thank you. Good, thank you. Thank you.